Okay, so whenever we join a heavily doped p-type material to this lightly doped n material, there will be always a depletion layer, and this depletion region will be more in the low doped area. So whenever a power supply is given across drain to source, there will be a current flow. This current flow will be because of the charge carriers. These are electrons in our case of n channel. These charge carriers will be attracted towards positive side, repel from negative side, so there will be flow of charge carriers, and because of this charge carriers there will be a current id flowing from drain to source and back to VDS. So this is the normal thing which was happening. But now if I connect this terminal, which is a heavily doped p-type material, to the source terminal, what will happen, and what will happen if I go on changing VDS, that we'll see, and I will explain you in terms of graph also how it happens. So I hope you see it properly. So we'll plot those things. One is our VDS, drain to source voltage, VDS, and second is ID current. This is ID current, and this is VDS voltage. So I'll write it here as VDS. So on x-axis we are having VDS, on y-axis there is a ID. So what will happen if I go on increasing the VDS voltage? So as I go on increasing, when the potential VDS is 0, there will be no current in this path, and when there is no current, your graph will start from this location, that is at 0 position. As I go on increasing VDS, ID will increase because this is following a Ohm's law, which is equal to V is equal to I into R. So as I increase V, I will increase. So this current will go on increasing. Now after this point, what is happening? Let us see. When it reaches, or when current is increasing slowly and simultaneously, there will be a rise in the depletion region. This depletion region will be increased and will be more towards the drain region. Why and how? All these things I'll tell you. First thing is that actually in this case we are reverse biasing a PN junction. You can see to the N material, this is whole N material. To this N material I have given positive potential, and to the P material or P side I have given a negative potential. So actually we are reverse biasing this PN junction. So whenever a PN junction or diode is reverse biased, what will happen is that there will be a rise in the depletion layer. So depletion layer will go on increasing. This depletion region will be more in the low doped area. So depletion region rises. What is depletion region? Depletion region is the void of any free charge carriers. That area which is void of any free charge carriers. That means this area does not have any free charge carriers. Because of a rise in the depletion region, the current which was flowing because of this charge carriers, that is electron, was flowing, now will be flowing in this way. That means they will try to travel in between the region, between the two depletion regions. So because of which we can say actual cross section area has been decreased. So what will happen due to decrease in cross section area? Last time I had told you about V is equal R is equal to rho L by A. What is rho? Rho is the resistivity of any material, L is the length of that material, and A is the cross section area. In our case we are decreasing the cross section area because of depletion region. So as cross section area has been decreased, your resistance will go on increasing, and as resistance increases, your this graph which was supposed to go straight will now start bending, and this bending is because of a rise in the resistance. So why there is a bending in VDS graph? Because previously what was happening, as I increase V, I was increasing, R was not increasing, but now R also will start to increase. Now current, as much R increases, that much current will not increase, or the increase in the current will now reduce. So increase in the current has been reduced, and you can find the slope. As I go on increasing V, more and more depletion region will be created, and less cross section area, more and more resistance increase, and less current increase. So at some point, at a point when both these depletion regions come so much together, that I call it as a pinch of condition. In that pinch of condition, which is we are keeping the distance between the two fingers as small as possible, that is called as a pinch off. So whenever it has been reached, after that there will be no rise in current, but resistance will be now directly proportional to V. So now it will be V will be directly proportional to R, because of which you will find no current rise, current will be constant, and you will find a flat graph. Even if you still try to increase VDS, now increasing VDS, what was happening? These charge carriers were trying to travel from negative to positive, and in between they are obstructed by this depletion layer, which is a charge carriers or charge ions not carriers but ions. And because of this ions, the electrons which are having a huge kinetic energy, they will collide to these ions and will release more number of electrons, and all these more number of increased electrons will now travel towards positive. That means your current has now increased. So after some time you will find the same graph going in the upside. That means what? Your current is rapidly increasing. This rapid increase in the current, we call this as a avalanche breakdown. AVALANCHE, avalanche breakdown. Now this avalanche breakdown is always because of the collision of charge carriers to the stable ions. Because of that there will be a avalanche breakdown. After this breakdown, you have to assume that your FET is damaged. So it will not again, you cannot use that again. So this is what the characteristics you will find. What you have seen here, as I increase voltage, current increases in this path called as a ohmic region. Ohmic region, because it follows Ohm's law. V is equal to IR is followed in this region. That's why we call this as a ohmic region. When we have reached to this point where the distance between the two depletion region is at the minimum, that point is called as a VP point or pinch of voltage. After this pinch of voltage, there will be no rise in current, but the graph will be almost flat. So this region is actually called as a active region, saturation region. It is called as a saturation region, and normally we make our transistors, that is FET, work in the saturation region. So this is what happens whenever we are doing this process of giving biasing. Have you understood ohmic region, saturation region, and avalanche breakdown or breakdown region? These are the breakdown regions. Now I'll explain you the same process, but with some negative voltage given between VGS. Now I have given some negative voltage to gate. Now that voltage is called as gate to source voltage, VGS. After giving this some negative voltage, and again we'll be starting VDS change from 0 to some high value. So at 0 potential there will be no current flow. So as I go on increasing the VDS, my current flow will start. At the same time, the depletion region will now go on becoming bigger. So because of that, you will find your graph has a more resistance. As there is more resistance, your graph has changed. Last time I told you, if I increase the resistance value, your VI characteristics will be more and more towards a flat line, which will be less ID and more VDS. So again, this By increasing the potential VDS, current will increase during ohmic time. After that, current will stop increasing and your characteristics will look like this. After this point, that is after pinch off point, the only voltage change will increase the resistance. So this is about the graph where I have given some VGS value of minus 1 volt. Let us assume it. Third time we are changing this VGS to minus 2 volt and again repeating the same process. What we will be getting initially, only there will be more depletion region, so initially only there will be less cross section area and less current. So your graph will not be straight but almost will be equal to flat, because as I increase the depletion layer, the cross section area has been decreased, which increases the resistance R, and due to this increase in the resistance R, you will find your graph becomes almost flat again and a avalanche breakdown. Now the VP which has reached is now has come here. So for 2 volts, for 3 volts I can do this. This was for VGS is equal to minus 1 volt. Here VGS is equal to minus 2 volt, and at the bottom it may be VGS is equal to minus 5 or 7 volts. So this is what the characteristics you will find in the FET. This type of characteristics is also called as output characteristics, or it is also called as a drain characteristics. Drain characteristics. So have you understood this graph, how it is happening? Secondly, you can find VP is not exactly at the vertical line. Why? Because whatever the staff is